What if the key to building the next generation of quantum computers lies in particles that behave like they're carrying bricks instead of zipping through space? Researchers in Japan have uncovered a mind-bending phenomenon involving heavy fermions, electrons that act as if they're burdened by an unexpectedly massive effective mass. These particles, which emerge when electrons in a material strongly interact with localized magnetic moments, aren't just theoretical curiosities. They might just be the missing puzzle piece for revolutionizing quantum computing. But here's where it gets controversial. The team discovered that these heavy electrons aren't just sluggish. They're quantum entangled in a way governed by Planckian time, the smallest possible unit of time in physics. And this is the part most people miss. This entanglement doesn't vanish at room temperature, making it a tantalizing candidate for practical quantum technologies. The study focused on a compound called cerium rhodium tin, CERHSN, part of a rare class of materials with a quasi-Kagame lattice. Imagine a network of triangles and hexagons that create a kind of geometric frustration, forcing electrons into unusual states. When the researchers measured CERHSN's electronic properties, they found something extraordinary. The material's heavy electrons maintained their strange behavior up to nearly room temperature, with lifetimes approaching the Planckian limit. This isn't just a lab oddity. It's a sign that quantum entanglement can be harnessed in solid-state materials under conditions we might actually use in real-world devices. Dr. Shinichi Kimura of Osaka University, who led the study, explains that this discovery bridges a critical gap. For the first time, we've directly observed how Planckian time controls the entanglement of heavy fermions in a quantum-critical state. He says, this could redefine how we design quantum systems, moving beyond theoretical models to tangible applications. The implications are huge. If we can manipulate these entangled states, we might build quantum processors that operate at higher temperatures or with greater stability than current designs. But let's pause and ask, could this be the future of quantum computing, or are we overlooking hidden challenges? Critics might argue that scaling these effects to functional devices remains a distant dream. After all, turning a lab breakthrough into a commercial product often requires overcoming decades of technical hurdles. What do you think? Is this the next leap forward, or are we chasing a mirage? Share your thoughts in the comments below. The research, published in NPJ Quantum Materials, opens a door to understanding how quantum entanglement and heavy fermion physics intertwine. With further exploration, these findings could unlock new avenues for quantum information processing, from ultra-efficient data storage to secure communication networks. As the field evolves, one thing is clear. The dance between heavy electrons and Planckian time is just beginning, and the possibilities are as vast as they are unpredictable. Reference: anisotropic non-Fermi liquid and dynamical Planckian scaling of a quasi-Kagame Kondo lattice system. By Shinichi Kimura et al. 5 August 2025, NPJ Quantum Materials, DOI 10.1038/S41535/0797W. Funding: Japan Society for the Promotion of Science. Never miss a breakthrough. Join the SciTech Daily newsletter to stay ahead of the curve.